The F-35 is built around one single idea. Radar cannot find it. Its coding and geometry reduce its radar cross-section to the size of a metal marble. Iran didn't use radar. They listened to the F-35's own transmissions, and the aircraft had no way of knowing it was being heard. The F-35's stealth coding defeats radar. It does nothing for what the aircraft broadcasts. Radar works by sending electromagnetic energy toward a target, waiting for that energy to bounce back, and measuring the return. The entire stealth engineering program exists to break that single chain. The F-35 breaks it two ways. First, its skin is covered in radar-absorbent material that converts incoming radar waves into heat. The energy arrives, gets absorbed, and dissipates instead of bouncing back to the radar antenna. Second, the airframe geometry is shaped so that whatever energy the RAM does not absorb reflects away at angles that never return to the transmitting radar. Together, these two features reduce the aircraft's radar cross-section to roughly 0.001 square meters. That is the electromagnetic signature of a metal marble. A ground-based radar designed to track a conventional fighter at 200 miles might not detect the F-35 until it is within 20. By then, the radar operator has seconds to react. The missile system fed by that radar may never receive a usable track at all, but the coding and the geometry only solve one problem. They defeat energy coming in from outside. They were never designed to hide what the aircraft itself puts out. During every combat sortie, the F-35 operates its APG-81 active, electronically scanned array radar. And this is the pilot's primary sensor for detecting threats, mapping terrain, and tracking targets. The APG-81 uses a low probability of intercept waveform, spreading its transmitted energy across frequencies and time to make detection harder. But harder is not impossible. The radar still transmits energy outward at the speed of light. A receiver tuned to the right frequency band, positioned in the right place, and built with enough sensitivity can detect that transmission at ranges the LPI design was not built to cover. The radar is not the only system talking. The F-35 carries an IFF transponder, identification friend or foe, that responds automatically to interrogation signals. Every time a friendly radar, ground station, or airborne platform sends an interrogation pulse, then the F-35's transponder answers with a coded signal on a known frequency at a known interval. This is not optional. In a complex airspace with dozens of Allied aircraft, the IFF transponder is what prevents a friendly missile from targeting the wrong jet. Turn it off and the risk of fratricide becomes unacceptable. Leave it on and every response is a precisely timed, precisely formatted emission that any receiver tuned to that frequency can log. Then there is the Multifunction Advanced Data Link. MADL connects F-35s to each other in a directional, low probability of intercept beam. It is designed to be difficult to detect from outside the beam's narrow arc. But the aircraft also carries Link 16 for communicating with legacy platforms that cannot receive MADL. Link 16 is omnidirectional. It transmits in every direction simultaneously. In a passive detection environment, operating Link 16 is functionally identical to broadcasting a position beacon. The AN/ASQ-239 electronic warfare suite rounds out the emissions picture. It scans for threats, classifies radar signals, and manages countermeasures. Doing this requires receiving and processing electromagnetic energy from the environment. The system itself is largely passive, but its integration with other onboard emitters means the F-35 in combat configuration is an electromagnetically active platform at all times. The F-35 in cruise with every system running. The APG-81 cycling its waveform across the spectrum. The IFF transponder answering interrogations every few seconds. MADL synchronizing with the formation. The EW suite scanning and cataloging. Every system performing exactly as designed. Every system putting energy into the electromagnetic environment. The radar warning receiver shows nothing. No threat radar is painting the aircraft. The cockpit is quiet. The pilot has no indication that anyone is listening. Every system doing its job. every system telling anyone with the right antenna exactly where the aircraft is. A passive receiver does not transmit anything. It cannot be detected by the aircraft it is tracking. It cannot be jammed because there is no emission to jam. It cannot be targeted by an anti-radiation missile because it radiates nothing. It simply listens. And listening, it turns out, is enough. A single passive receiver pointed at the sky can determine the bearing to an electromagnetic emission. It knows the direction the signal is coming from, but not how far away the source is. One receiver gives a line. Two receivers separated by enough distance give two lines. Where those lines cross is the emitter's position. Three or more receivers produce a continuously updating triangulated fix that tracks the source as it moves. The accuracy depends on geometry and processing speed. At 500 knots, an aircraft covers roughly 1.4 miles every 10 seconds. A triangulation fix that takes 30 seconds to compute places the aircraft over 4 miles from where the calculation says it should be. That gap determines whether the track is useful for situational awareness or precise enough for weapons employment. More receivers, faster processors, and shorter baselines between stations tighten the fix. Fewer receivers and slower processing produce a track that says something is there, but cannot say exactly where with enough precision to shoot at it. The IFF transponder is the most reliable emission to track. It transmits on known frequencies in a known format at predictable intervals. A passive receiver tuned to those frequencies does not need to classify or decode the signal. It only needs to log the bearing and the timestamp. Each interrogation cycle produces a fresh data point. The track builds itself. The APG-81's LPI waveform presents a harder target. It was designed specifically to resist detection by radar warning receivers on enemy aircraft, but a generic airborne warning receiver and a dedicated ground-based passive collection system optimized for a specific waveform are not the same thing. A ground-based system with a large antenna aperture and long integration time can recover the total transmitted energy regardless of how the waveform spreads it across frequency and time. The energy is conserved. Spread it thin enough to fool one kind of receiver, and a different kind of receiver simply listens longer and collects it all. The F-35 flew through the receiver network's coverage area, broadcasting its presence with every system cycle. The aircraft's threat warning systems registered nothing. No radar painted it. No missile guidance signal triggered an alert. The electromagnetic environment, as far as the cockpit displays were concerned, was clean. The AN/ASQ-239 detected no threat because the system observing the aircraft was not transmitting anything to detect. Iran has been building toward passive detection capability for over a decade. The F-35 detections were not an accident. They were the first operational confirmation that the architecture works. Iran's air defense network is layered. At the long-range tier, the Ghadir radar system operates in the VHF band at frequencies around 150 MHz. That translates to a wavelength of roughly 2 meters. The F-35's radar absorbent material and edge geometry are optimized to defeat X-band radar, which operates at wavelengths measured in centimeters. A surface designed to make centimeter-scale waves disappear interacts differently with waves 2 meters long. At VHF frequencies, the F-35's radar cross-section grows measurably. The marble becomes something closer to a dinner plate. Not large enough to produce a fire control quality track, but large enough for early warning detection at extended range. The SEPR over-the-horizon system complements Ghadir by providing wide-area surveillance that cues the network to approximate locations of airborne activity. Together, these systems narrow the search space. They tell the passive receivers where to listen. The passive receivers are the critical layer. Russian doctrine has invested in passive detection systems for decades. The Kolchuga M and similar platforms represent a design philosophy built specifically to exploit the emissions of Western combat aircraft. Iran studied this philosophy, whether through direct acquisition, technology transfer, or indigenous development based on the same principles. Iran deployed passive receiver nodes positioned to provide triangulation geometry across its airspace. Multiple stations, separated by known distances, each logging emissions with precise timestamps and bearings. The display showing the F-35's position updating every few seconds. Operators watching the track develop across the screen. The bearing lines from 3 stations converging on a single point that moves steadily across the map. The decision point arriving. Is this track accurate enough to engage? The active radar battery standing by. Turning it on confirms the track but tells the F-35 it has been found. Staying passive means watching the aircraft transit without firing. Both options cost something. This is the critical distinction the entire engagement hinges on. Detection is not targeting. A passive track from IFF emissions and intermittent radar detections provides position and heading. Converting that into a firing solution for a surface-to-air missile requires either active radar illumination, which the F-35 would immediately detect through its AN/ASQ-239, or a passive track accurate enough to meet the missile seeker's terminal guidance requirements. Most passive systems produce tracks accurate to within a few miles. Terminal guidance for a modern SAM requires accuracy within a few hundred meters. The gap between those two numbers is the distance between observation and a kill. Iran could see the F-35. Whether they could kill it based on what they were seeing is a different question with a classified answer. The F-35 program's response to passive detection is not a new coating or a redesigned airframe. It is a doctrine called emission control, and enforcing it in combat makes the aircraft significantly less capable at the mission it was built for. EMCON doctrine requires pilots to manage which systems are active and when. Reduce the APG-81 to standby, and the primary radar emission disappears. But so does the pilot's radar picture. Suppress the IFF transponder, and the most trackable emission goes silent. But every other friendly aircraft and every ground-based air traffic control system in the theater loses the ability to distinguish this F-35 from an enemy contact. Shut down Link 16, and the omnidirectional broadcast stops. But coordination with every legacy platform in the strike package ends with it. MADL's narrow beam survives EMCON better than any other system, but it only connects F-35 to F-35. The rest of the network goes dark. The F-35 was never designed to operate as a solo penetrator flying in silence. Its entire combat concept depends on functioning as a network node. It receives targeting data from satellites, AWACS platforms, and other aircraft. It fuses that data with its own sensors and shares the result across the formation. EMCON silence breaks this architecture at the moment the architecture matters most. A strike package entering hostile airspace with every F-35 in full emission silence is a formation of individually capable but collectively blind aircraft, each one unable to share what it sees or confirm what its wingman is doing. The IFF problem has no clean solution. Mode 5. IFF is encrypted to resist spoofing and interception of the coded content. But the encryption protects the message, not the transmission event. The emission itself, its timing, its frequency, and its bearing are the trackable data. A passive receiver does not need to read the code. It only needs to detect that a transmission occurred, from what direction and at what time. Encrypting the content is like whispering a secret in a quiet room. The words may be unintelligible, but everyone in the room knows someone is whispering and exactly where they are standing. Full EMCON silence eliminates the passive track. It also eliminates the radar picture, the network coordination, the IFF protection, and the data link that makes the F-35 more than a single aircraft with a single pilot's eyeballs. Partial EMCON reduces emissions, but does not eliminate them. The IFF still cycles. The passive track still updates. The receiver network still logs the bearing. The aircraft is quieter, not silent. The stealth that cost over $400 billion to develop defeats one detection method. The adversary moved to a different one. The aircraft cannot stop transmitting without stopping operating. Bye for now.